All right, so now let's talk more specifically about carbon-13 NMR. Like I said, it's a little bit more simple than hydrogen NMR, so I want to start with this one. Okay, so here is what we can kind of expect to see for a carbon-13 NMR spectrum. Again, notice that we have at the bottom the frequency measured in ppE, also called chemical shift. You see we have these peaks here, right? So we have each one of these peaks, so we have 1, 2, 3, 4, 5, 6 distinct peaks here. And then also the information that's given up at the top are these numbers. These correspond to the integration of these peaks, and we'll talk about why that's important here in a second. But let me just point out that this peak here has an integration of 1 compared to this taller peak here, which has an integration of 2. So that's what the information is there. It isn't the height of the peaks. If we zoom in very closely, we see that these peaks are actually shaped kind of like this, like a triangle. And so it's actually the area underneath those peaks, not the height, that's important. All right, but there's 3 important pieces of information in any carbon NMR spectrum, okay? First of all is the number of signals. So again, that's the number of distinct peaks that we see in our spectrum. So here, 1, 2, 3, 4, 5. Notice that if I zoom in here, there are these 3 peaks right next to each other. 6. So in this case, there are 6 distinct signals, 6 distinct peaks. That's going to be this important piece of information. We'll talk in depth as to why that is, but just to point these things out. Next is the signal locations. So where on this spectrum they absorb. Okay, so these all the way down at 50, and then we have one all the way over at 200. So just like with our IR, we'll see that different functional groups absorb in different regions. And so based on where that signal is located, we can gain some information about the nature, the where that carbon is located within a molecule, what functional groups is it attached to. And then lastly is, again, that signal intensity, or I think the key word to remember here is integration, the area under that curve. And again, that's what these numbers up here correspond to. And again, just to sort of zoom in here and point this out, you can see kind of in the height, although, you want to rely on the numbers. This little peak here corresponds to 1. Notice that these ones are run into each other. That's just kind of because they're so close to each other, there's not much you can do. Whereas this peak over here has an integration of 2. Okay, so we'll talk about why that's important. But those are the main things that you're going to pick out when you start looking at your NMR spectra. Okay, and at the end, we'll go and see how this matches to this particular molecule. All right, so first of all, the number of signals. Why is that important? So the number of signals in a C13 NMR spectra indicates the number of chemically equivalent carbons. Okay, so what the heck does that mean? This is going to kind of be reminiscent to when we talked about stereocenters and how we said that a stereocenter was something with 4 different bonds. Well, what did it mean to be 4 different bonds? Right? It wasn't just that the next door neighbors had to be different. It was sort of everything that you were looking at. It was kind of more of a principle of symmetry. It's the same thing here. So here's 2 examples of compounds that have only 1 chemically distinct set of carbons. So in benzene, all 6 of these carbons are chemically equivalent. Okay, and what that really means is I can take any one of them and swap them, and I get the exact same molecule. I don't actually change the environment of that carbon at all, right? Because it's all about those carbon nuclei. They're sitting in a certain chemical environment, right? Like the amount of electrons and stuff, the amount of neighbors that they have. If you swapped any 2 of them, do you actually change that environment? In the case of benzene, no. They're all interchangeable because it's this perfectly beautifully symmetric molecule. All have the same number of bonds, etc. Bound to the same atoms. So for the NMR spectrum of benzene, all we would expect to see is this 1 peak corresponding to the fact that all of those carbons are chemically equivalent. Same with ethane. Again, in our NMR, C13 NMR spectra for ethane, we only have one peak because both of these carbons are chemically equivalent. If I picked one up and swapped it, I wouldn't change anything. I wouldn't change its environment. It's still bound to one carbon and 3 other hydrogens. There's nothing sort of weird going on there. Okay, so these are 2 examples of only having one set of chemically equivalent carbons. So you only expect one NMR signal. So let's look at a few other ones. So let's just take this step by step here. We get to 2-chloropropane. We have one, actually, let's just go through and label. We have 1, 2, 3 carbons. However, in our NMR spectrum, our C13 NMR spectra, we have 1, 2 peaks, corresponding to the fact that there are only 2 sets of chemically equivalent carbons. The one in red is chemically distinct from the 2 on either side, right? So carbons 1 and 3 are chemically equivalent. You could not swap, if you swap those, you wouldn't change the environment compared to 1 and 2, right? So if you swapped 1 and 2, carbon 1 is bound to, well, I don't even, it's not even as simple as the fact that it's bound to 1 other carbon and 3 other hydrogens, whereas this one's bound to a chlorine, a hydrogen, and 2 carbons. Because again, it has to do with all sorts of symmetry. And so we'll see some more examples here. I will point out, notice that the integration is different, but we'll talk specifically about that in a second. So again, just looking at the number of chemically distinct carbons, we only have 2 in 2-chloropropane, which is why we would expect 2 signals. One of those corresponds to one set, and the other one corresponds to the other set of chemically distinct carbons. Okay? We go on over here. Now we have 2-chloro-2-methylpropane. Okay? And again, in our NMR spectrum, we only have 2 distinct carbons, 2 chemically distinct carbons. So we're only going to get 2 signals on our NMR spectrum. Again, we have the one that the chlorine's attached to. That's one of our signals. And now each one of these, 1, 2, 3 carbons are identical. If you swapped either one of them, they would be in this chemically equivalent environment. And thus we would expect all 3 of them to give us a signal in the exact same place. Okay, so we have only, so again, we're just counting the number of signals that we have and matching that to the number of chemically distinct carbons in our molecule. We have 2 chemically distinct carbons. And then note, right, this chlorine isn't a carbon, so it's not going to give us a signal in our C13 NMR. So remember, we're specifically focusing on carbons. We go down here. We have 4 signals, and so that's going to correspond to 4 chemically distinct carbons. Okay, so this is going to be a good example here. Here we have a CH3, and here we have a CH3, but they're not in the exact same environment. This is located 1, 2 away from this chlorine, whereas this is 1, 2, 3 away from this chlorine. So they're just not in this exact same environment. So even though they're both methyl groups, they're both CH3s, they would not be considered to be chemically equivalent. So this one's different from this one. Of course, this carbon's bound to the chlorine, so it's different from all the other carbons. And likewise, this one is also chemically distinct. Okay, and so this is why we would expect to see 4 distinct peaks on our NMR spectrum. Now, matching them up to which carbon's which, we don't know how to do that yet. I don't want you guys to get too hung up on that. That's not the purpose here. The whole idea is just to be able to figure out how many chemically distinct carbons are in a given molecule. All right, so now let's look at this one before we even look at our spectrum. See if we can't figure out how many chemically distinct carbons and thus how many sets of signals we would expect from this molecule here, okay? So first of all, I got this one. All right, that's the only carbon that's bound to a chlorine, so it's pretty easy to pick off. That'll be one set. What about these two? Are they distinct or are they equivalent? In this case, this is a pair of chemically equivalent carbons. Okay, they have the same environment. If you swapped them, you wouldn't change either of their environments. Same with these two here. Okay, so for this one, we would expect to get 3 signals, and that's indeed what we see from our NMR spectrum. Okay, and I just want to point out, let me get rid of this just to, in these two examples, right? So this is 4 distinct carbons, and this is only 3 distinct carbons. And again, this is what I was sort of like talking about going back to when we were talking about stereochemistry, right? Why is this carbon not a stereocenter? Because these two bonds, these two groups are identical, right? That's what would make that not a stereocenter. It's not bound to 4 different things. And in that same way, that same symmetry applies to this situation when we're talking about chemically distinct carbons. That's why these methyl groups are considered to be chemically equivalent. These carbons here are considered to be chemically equivalent, etc., because of the symmetry in this molecule. All right, so that's what the number of signals tells you. The number of signals in your C13 NMR spectrum corresponds to the number of chemically distinct carbons you have in a given molecule. So what about the integration? So you might have already caught this as we were going, but now just to point out, each of these peaks, so we've established that this is chemically distinct from these two. So now the integration value tells you how many carbons are corresponding to that particular peak, right? So the area under this curve here is twice as much as the area under this curve here, because this is corresponding to 2 carbons, whereas this is only 1 carbon. And so we can match this peak here must correspond to those 2, and this peak here to that 1. Okay, so that's the other piece of information. Not only does the number of peaks tell you information about your molecule, but the area under those peaks. Likewise, in this particular molecule, we said all 3 of these were equivalent, which is why the area under this curve is 3 times what the area under this curve is, right? And again, that's because this corresponds to 3 carbons, and this only corresponds to 1 carbon. Okay. In this particular example, all 4 of these carbons were chemically distinct. That's why I got 4 different signals. That means that each signal is only going to correspond to 1 carbon. So that's why the area under each of those curves is the same. All right, and then lastly, again, we said that this guy was distinct from these 2, was distinct from these 2, and that's why the area under these 2 curves is twice the area of this curve, because each of these curves correspond to 2 carbons, and this only corresponds to 1 carbon. All right, so number of signals tells you how many chemically distinct carbons there are in a molecule. The area or the integration of each signal tells you how many carbons that signal corresponds to. So now where in the spectrum they lie, again, kind of similar to IR, where in the spectrum, where in your NMR spectrum you see a peak tells you a little bit about the environment of that carbon, okay? This portion, we're going to call it the alkyl portion. These are all your sp3 hybridized carbons. So methyl groups, ethyl groups, all those good things. will fall in the 0 to 50 range. 50 to 100. This is where you'll find these sp hybridized carbons, so triple bonds, as well as when carbons bound to something fancy like a carbon, an oxygen, could also put a halogen in this category here. Whenever carbon's bound to something electronegative, that would fall in the 50 to 100 range. The 100 to 150 range, these are sp2 hybridized carbons. Okay, this is kind of, this can be very helpful. We deal with benzene rings and all that good stuff a lot in organic chemistry. So watching out for peaks in the 100 to 150 range can give you a good idea as to whether or not you're expecting to see a benzene ring or any other sort of a double bond. And then lastly, and this is one of the most signature ones, the 150 to 220 range is specific to carbonyl carbons. So anytime you see something in the 150 to 200 range, 220, you know it's a carbonyl carbon. Okay, so having something fall in one of these two here can give you a really good idea as to what your compound is, even before you start looking at integration and number of chemically distinct carbons and all that good stuff. So just to give some examples, right? So again, benzene, we saw first, notice that that has its peak. It's one peak because it's got all of those 6 carbons are chemically equivalent, but it falls in that 100 to 150 range. Whereas our ethane, our kind of boring alkyl group, that's down here in the 0 to 50 range. We have a triple bond in the case of hexyne, 3-hexyne. And so that gives us a peak in the 50 to 100 range. This would also be where you have any sort of electronegative group as well. So an oxygen, a nitrogen, or a halogen, you would expect it to fall in that range. And then again, anything north of 150 is characteristic to that carbonyl carbon. So if we want to look at this spectrum in particular, we can actually assign, well, I guess we could do it anyway based on the area, but we can further convince ourselves that this makes sense, that this carbon here corresponds to this 210 peak, right, all the way downfield. And then these 2 carbons here, which are chemically equivalent, correspond to this here. Notice that that falls in that upfield of 50 range because they're just methyl groups. Okay, so that's where on the spectrum it lies, tells you a good bit about the carbon. So now let's see if we can't pick apart and figure out what's what on this particular example. So this is our original one that we talked about. So now let's see if we can't apply everything that we learned and match some of the peaks here. Okay, so first steps first, and this is going to be a really important skill, is to identify how many chemically distinct carbons in a given molecule. Okay, our spectrum tells us that there should be, I think we counted 6, right? 1, 2, 3, 4, 5, 6. So we want to make sure that that's the case, that we can see that above. This is a good idea to pause and to practice, and then I'm going to go through it here. So first of all, we notice a line of symmetry going through this molecule. So that tells us that everything on one half has a partner on the other half. So specifically this guy here and that guy here match. These 2 match. These match. I already did cyan. And these match. What about the ones that lie actually on the line? I'm gonna get a different color. I'm not used. Okay, they are not chemically equivalent, right? This and this one are not the same thing. So these are going to be their own lonesome peaks. We have one at the top, and then our last one at the bottom. So indeed, we have 1, 2, 3, 4, 5, 6 distinct groups, or chemically distinct carbons, groups of carbons. And then we can actually go ahead and assign our integration as well, because they have, based on the number of partners that they have. This is in a group of 2, green's in a group of 2, same with the blue, same with the orange, and then these ones each have 1. Okay? So now let's see if we can't match what's what. The easy ones to do are going to be the ones in the extremes. So this all the way north of 150, remember that that is characteristic of a carbonyl carbon. So that's going to be our cyan carbons there. And then likewise, we have one sitting around 50. That's going to be just those boring old methyl, ethyl, whatever carbons, alkyl carbons. So that's going to correspond to the green. Okay. In here, we can't go and assign these carbons uniquely necessarily, other than to say that these are our benzene carbons. And we do know that these half-height carbons here will correspond to either the purple or the gray, right? So the ones that are an integration of 1 compared to the blue and the orange, which are an integration of 2. Actually going through and divvying them up isn't necessarily, I mean, that might be a good exercise at some point in advanced NMR, but for now, this is sort of as good as we can get, and that's perfectly fine. This would still be very helpful in identifying if you were given this signal, going and figuring out what molecule it corresponds to, okay? How this would be done is you would be given like the molecular formula for the molecule, C10, 10, H whatever, O2, and so you'd have sort of this idea, and then you could work backward. It's kind of like a little puzzle.